Let's get started. Welcome everybody to today's meeting. We are very happy to have Sofia Vallecorsa from CERN here. Sofia got her PhD from University of Geneva. She then went on as a postdoctoral researcher in Israel at Technion. After that, she received a Maria Vöckling Fellowship, where she went to back to Geneva. And now she's been at CERN for a while as a researcher. And she will tell us about her work or work in the group of quantum machine learning. Please go ahead, Sofia. I should also say, if you have questions, please feel free to interrupt her or to ask your questions at the end.
Okay, thank you. Well, first of all, I would like to start by saying that this talk will not give you an introduction on quantum computing. I'm assuming you have the basis. I did prepare just in case there are, very basic doubts that you might have. I do have some slides, so we can also discuss that. But those are very, very basic concepts that I have put there just in case among the supplemental material. What I want to do is to give you an idea of what it means to use quantum computing to do machine learning and explain the first experiments that we started already now the last couple of years at CERN. So this is the title of my talk. I will just start with a very, very brief introduction about CERN for those of you who might not have an energy physics background. So CERN is one of the major labs, in fact, one of the major experimental scientific infrastructure that is at the border between France and Switzerland, close to Geneva. You can see its main facility is the LHC Large Hadron Collider, which is a 27-kilometer accelerator. And there are 4 major experiments that are located around the LHC rings. So CERN is the LHC experiments are more or less collecting now something like 200 petabyte of data per second. This is a huge amount of data that needs to be processed, and that is going to, you can see here the 4 experiments, that is going to increase even more in the coming year. The LHC schedule is planning to have a major upgrade and start a high luminosity run in just a few years from now, which it's called the high luminosity LHC, and that will bring a huge stress in terms of computing resources as far as data analysis is concerned. All the full data analysis chain, processing chain is concerned. You can see an example here. Those were estimates that were produced a few years ago. They've been published in a community white paper couple of years ago, and give an estimate of the storage and computing capabilities for one of the experiments, the CMS experiments, and compare what are expected to be the requirements for the high luminosity runs with respect to what we have today. And we are talking about huge increase, orders of magnitude, in fact, increase in both cases. Now, this is not necessarily something that we want to solve with quantum computing, but it is the major problem that we have today. And what we want to do today now is to understand how much quantum computing could be in the future one of the solutions to this kind of problem. Because of this, last year, around September, CERN approved the Quantum Technology Initiative, which is aimed exactly at trying to understand what are the challenges related to using quantum technologies. And as you see here in the bottom of the slide, I'm not talking about quantum computing only, but I include also the other typical branches that are identified in this field. So anything that has to do with hardware development and sensing, so the vectors development for high energy or low energy physics, communications, and aspects that are more related to theory, so direct quantum simulations, for example. and anything that is more related to information theory as well, quantum information. Now, the idea is to, on one hand, coordinate and push the activities within CERN and the community across those different fields, but at the same time, because there are a lot of initiatives that are going around in the different member states in Europe and beyond, at different levels. And so the other goal is really to coordinate with all those different initiatives in order to help structure a well organized ecosystem. Let's say that the 4 different major branches have already had a few collected quite some work at CERN. Those have been mostly first, let's say, experimental tests. What you will see today is everything that's related to everything. It's examples that are within the field of quantum computing. But as I mentioned before, there are activities that are developing. For example, they are aimed at developing high sensitivity calorimeters for sensing, or studying quantum communication. We have a repeater from the OpenQKD network, for example, that is installed at the CERN data center, and also applications in theory. Part of this work had already started CERN within the CERN Open Lab quantum program, and you can find more information at the websites that you see linked below. In particular, the official can you see my pointer, by the way? I never know.
Yes, we can. Thank you.
Okay, great, because it will make it easier. So the official QTI website is listed here, and we are still building it at the moment. So you'll probably find more information on the Open Lab site. So this is the outline of the talk. As I mentioned before, I would like to start with some more generic introduction about quantum machine learning, what's interesting about that, what are the challenges related to that, how do we go about it, and then I will go to some practical examples, so some network models that we've already developed and tested, etc. Before going there, I just wanted to point out that when we talk about quantum computing, we are talking about that there are many different approaches that we can take. So I'm not even talking about hardware. Of course, there are different hardware technologies that can be used to build qubits, semiconductors, ions, or whatever. Here, the point that I want to make is differences at the programming level. So what's usually called the universal quantum gate approach is everything that has to do with qubits, so digital quantum information that can be initialized and processed through a series of gates, which are unitary gates that represent the different operations that we can run on them. This is the approach that is followed by most of the major companies that are well known about in the field of quantum computing. You see just some names there. Quantum annealing is another approach. This is the idea of implementing a problem as the Hamiltonian in a quantum system, and following the evolution of the system to lower temperature Gibbs states in order to find equilibrium points that corresponds to the solutions, basically, of the problems we have implemented. And this is a very powerful tool that can be used to all sorts of optimization problems. It has been also applied in some cases to train networks, in particular to implement quantum Boltzmann machines, for example. But I will not talk about this in this talk today. There is also another approach, which is based on optical systems. So the photonic quantum circuits, in principle, it's very the approach is very similar to what's done with semiconductor hardware such as IBM, Google, or Rigetti. What's interesting for us is the fact that because the information is encoded in continuous variables, the representation of problems, such as many that we have in our field, is straightforward, because in many cases, what we want to do is to directly reproduce, for example, simulate the continuous variables, and this is the approach that is used by Xanadu. And then you will see an example of this. Okay, so what do we mean when we talk about quantum machine learning? This is actually can be depending on the context, can be a rather generic name, in the sense that there are basically two major things that you might be referring to when you're talking about quantum machine learning. And this is, on one hand, the idea of using machine learning or deep learning models to improve quantum computing, so to develop new algorithms, for example, or to improve error correction techniques and to optimize quantum circuits. But more often, what we mean when we talk about quantum machine learning is the idea of using quantum computing to speed up machine learning models at the training level or at the inference level. And the idea behind this is the fact that more in general, a quantum circuit is a differentiable circuit. It means that can be optimized using, for example, methods such as stochastic gradient descent, and then it can be, and this can be naturally interpreted in the same way a machine learning model would be, and that is why this technique, this field has been developing very, very quickly in the last few years. Of course, what is important as far as any quantum algorithm, but in particular for quantum machine learning, is the idea of quantum advantage. And I would say that in case of quantum machine learning algorithms, the problem of quantum advantage is it's even more complex than for standard algorithms. Everything, I will get back to this in just a few slides after I give you a little bit more of information, but you will see that definition of quantum advantage in the case of quantum machine learning is very tricky, and it's related to a lot of choices that have to be made along the way. So in practice, what you will see here is everything that has to do with the second idea that I introduced about quantum machine learning. So using quantum computing or quantum computers, quantum circuits as trainable circuits, as trainable models that can learn different tasks from the training data. Now, if we want to do this, of course, there are a few practical, questions that need to be answered. Now, I assume that this is an audience that is expert on anything that has to do with machine learning and deep learning, and I will not. I will use concept. I will not explain anything about that. I would like to point out a few issues that are typical of the development of any new deep learning or machine learning based application, and that need to be addressed in specific terms also in for a quantum and in particular for a quantum approach. So well, you see a few of those questions listed here in green. Well, the first obvious problem is how do we solve the problem of data loading? In most cases, quantum machine learning algorithms are used to analyze classical data. Now, this is not necessarily always true. There are cases in which you might want to develop algorithms that are analyzing quantum data. But in general, for most of the applications that are being studied today, this is not the case. And therefore, the idea of finding efficient techniques to do embedding of classical data into quantum circuit, it's actually critical to the performance of the model, of the quantum QML model that is being trained, that is being developed. Another typical issue is nonlinearities. Now, in particular, as far as the qubits approach is concerned, it is very difficult to represent nonlinear operations in quantum circuits. This might, depending on what are the choices that are made in terms of data representations. So, how do we represent the classical data? So the previous step, how do we represent the classical data into our quantum circuits? There might be very, let's say, complex circuits or approaches that need to be introduced in order to represent nonlinear operations. That might result, for example, in rather deep circuits that necessarily then become harder to be to run on real hardware, at least for now. The problem is slightly simpler in the case of continuous variables. The continuous variable approach, so the photonic quantum computing approach, and I will talk about it. I will show you. I will talk about it later. And then there is, of course, your problem of convergence. This is something that has been deeply studied for classical models. In the case of quantum computing, what we are doing is mapping classical data and algorithms into a higher dimensional space, the Hilbert space, and studies, let's say, characterization of the behavior of models and gradients. For example, in the case of optimizations via stochastic gradient descent is critical. One of the first one of the first studies that was done a few years ago was, for example, warning or about the fact that problems such as barren plateaus and vanishing gradients, so regions of the phase space in which gradients become very, very small, and any optimization approach will, any gradient based optimization approach will find very, very difficult to get out of those plateaus. So that this problem would be even worse in case of a quantum model, in particular when the number of gates, so the depth of the model becomes increases. It's very interesting to see. So this is, for example, one of the area that has attracted a lot of work and a lot of research. And I'm mentioning here some work that was published just a couple of months ago by a group at the IBM and ETH. They try to characterize and measure in some way the effect of barren plateaus and compare the behavior of very simple classical networks to quantum networks, and try to quantify the risk of ending up in those areas, and therefore stopping the not stopping, but reducing the probability of convergence, the quality of the training. And they propose interesting methods based on information theory that tend to measure the probability of running into those barren plateaus by measuring the eigenvectors of Hessian matrices. What I find is that, you can see here an example training that compares loss functions for a classical neural network. This is a classification task that run on, I believe, the IRIS dataset, and compares the classical network to quantum models with two different set. I mean, with a simple and a slightly more complex architectures, which includes additional quantum features such as entanglement. And in particular, this work is also interesting because they compare their simulated data to runs on real hardware. I don't mention this explicitly here, but when we talk about studies about quantum computing, we need to have clear if we're talking about the ideal case, so the ideal theoretical scenario in which we have access to a large number of qubits with stable setup, without decoherence problems, without errors, or the case in which we are talking about realistic setups, realistic hardware, near-term devices in particular, that are instead affected by instability of their qubits, and therefore a certain set of errors that require correction or mitigation techniques. I will not go into this detail, but it's also interesting to note that because of the stochastic nature of training, there's speculation that quantum machine learning models could be more robust about against error problems, or at least against some sort of errors, quantum errors, because from the classical, from our classical experience, we know that some sort of noise contamination can be beneficial, actually be beneficial to the training process. Okay, so the way models are today implemented. Yes, please.
Is there a simple physical intuition for why quantum machine learning tends to run into the problem of getting stuck or running into saddle points? So are there just more saddles in the loss landscape, or is it more likely to run into saddles? And why are these overcome when you include
yes, the idea is that they're more likely to end up into secondary, into those flat regions. Okay, but it can change very much. So a way of characterizing this again is building the Hessian matrix for your phase space, and try to see how many. Sorry, I should have explained this better. And try to see how degenerate this is. So the more the eigenvalues of your matrix are clustering around 0, so you have more saddle points, more flat points, the more difficult the training becomes. The more your spectrums is not degenerate, so the more you end up with eigenvalues that are different from 0, the better the chances to actually get convergence, which is exactly what you see in this. This is a relatively simple use case that is chosen, and actually the architecture of the network is also chosen in such a way that this behavior is highlighted. But you see clearly that for networks, so the color match between those two plots. So the case in which the quantum networks have a larger set, have a non-degenerate spectrum, converges better. This is one way of looking at this.
Yes, and so you said this can be done, for example, by including entanglement. So why does entanglement break the?
No. Yeah, no. Let me. There is no one-to-one correlation. Okay. One intuition is the fact that introducing entanglement is introducing correlations that we cannot describe classically, right? So that is what it means to introduce entanglement in your network. In some sense, it's like trying to improve the representational power of your network. You are adding possibility or the capability of reproducing more and more features or of your phase space, more complex features of your phase space. Now, this is not necessarily directly correlated to this effect in particular, but it's one of the, together with other quantum effects, it's one of the ingredients that people are trying to correlate to the quality of the final result, to the convergence in order of the network, in order to simplify the way model QML architectures are designed. So unfortunately, there is no direct, let's say, or definitive answer concerning this for now.
Okay, thank you very much. There was a question by Alexei. He addressed his hand, or they addressed their hand. You can feel free to mute yourself and ask.
Hi, sorry. I mean, it might be an easy question that, as was said, was not explained. But I mean, in general, if you could just point me in the right direction. I mean, in general, quantum computing deals with linear systems, whereas neural networks are highly non-linear. So how do you marry those two things in the first place before you start?
Yeah. So this is I didn't go into the details of that, but it's a major problem. So, well, first of all, if you use continuous variable approach, you have the possibility of introducing non-Gaussian gates that can be used to build nonlinear activation functions, for example. But more in general, what you can do, well, there's different things that you can do. You can try to decompose, for example, that's two things. One is the fact that in most cases, and also in the applications that you will see here, what we are doing for now is to go from our classical models and trying to build their quantum version. Now, this is what most people do today, but it's not necessarily the best way to actually use quantum computing. In this approach, what you can do, for example, is to try to replace nonlinear activation functions with a series with approximations of those. This is one approach that you can take. Another way is to use kernel methods, and that's because and I will talk more about this later. The way we define our feature space, it's very, very important for the performance of the overall network. In addition, there are also quantum algorithms that can reproduce nonlinear behavior, but they can be applied only using some specific data representations, and that's not necessarily always suitable or for the problems, for the data that we need to embed, or it might just simply be so complex that it will cancel any possible advantage in terms of computation. I mean, there are different works that are exploring these different directions. So I will add to the slides some references maybe to this. If it's an interesting topic, I will, when I send around the slides, I will add references concerning this. This is a good point.
Appreciate that. Thank you.
Okay, sure. Other questions? Okay. I forgot what I want to say. Yeah. Right now, the approach that you will see that is used in most cases is a variational approach. Now, this is not specific to quantum machine learning. It's a general approach that can be used to solve different kind of problems at the quantum level with quantum circuits. What does it mean? A variational approach is using quantum circuit. It's represented here in this sketch on the right. It means to define a quantum circuit using that depends on continuous parameters that can be optimized. So a typical structure of a model, QML model, or a quantum circuit that is based on a variational approach would look like this. You would have an initial set of states. Here are they all initialized to 0, to one of the two states. You would have a part that is not, in general, not trainable, but we'll see that this is not actually always true, that embeds in the quantum circuit the classical data, the input data. Then there is the variational part, the part that is trainable, that is a circuit that performs a certain set of operations, rotation gates or others, that depends on a set of parameters, that can be optimized by a quantum loop or a classical loop. In this case, what happens is a classical optimization. After the circuit, the output of the circuit, the qubits are measured, the qubit states are measured, and the measurements are averaged out, because we are talking about measurements of quantum states that are then that have a probabilistic outcome. Sorry, sometimes I miss my English. Proper English. So they are averaged out, loss functions are built, and then we can optimize and produce updates with whatever methods we want. For example, stochastic gradient descent or other more fancier optimizers. And so you can see that this is a very direct map, a very simple mapping, a very direct parallel to classical machine learning. Gradient descent are in general the preferred optimizers in most applications, but they're not necessarily the only ones. For example, genetic algorithms could be tested, and in this case, those are gradient-free methods that might be interesting whenever we end up in problems such as variant plateaus that I mentioned before. The step of the data embedding can also be learned. So in this schema that you see here, it isn't, but it actually is something that can be very, very important and can make a difference in the performance in the final, for example, classification, regression, or whatever task that's run afterwards. This has been proven by several works. I list here one of them. This is relatively recent from last year's, but there's more work that has been looking into into how to design the optimal data embedding that takes into account not only the classical data, but also the quantum circuits that used for the specific task. Kernel methods are one of the most interesting topics methods that are being investigated today, and that's also because of what we mentioned before, the problem of introducing nonlinearities. I have already mentioned the fact that error mitigation strategies might be important. So this is a very important step that can change the performance of a model at the training level or at the inference level once it is actually run on a realistic setup. And before continuing, I also would like to mention the fact that all of this occurs today. Well, let's say all of the development steps is actually run on simulators, and simulators can be very slow. And so this is actually not a simple study to do, in the sense that if we would like for some configurations, and even without reaching a large number of qubits, so even at the level of a few qubits, like a few tens of qubits, not even, sorry, around 10 qubits, let's say, training a model can take days through a simulator. And so this is also, in fact, a factor that needs to be taken into account when we're doing development as far as QML is concerned. How do I advance? Yes. So all of this brings me back to what I mentioned before, what I wanted to say before about quantum advantage. Now, there is, of course, when we're talking about generic algorithms, usually you define advantage in terms of runtime speedup. Is the problem going to scale exponentially with respect to the size of the input? Is it going to scale logarithmically, polynomially? In the case of quantum machine learning, there are also other aspects that might be more important and we might want to take into account. Everything that is referred to as model complexity, for example, what I write there as representational power. In general, those models are much smaller than classical models in terms of number of parameters. So of course, this does not directly translate into the conclusion that a quantum circuit has in nature a higher representational power, but it could be indeed something that is related to the fact that the data is mapped to a Hilbert space. There is also what I mentioned before that is related to the way algorithms are today designed. We are probably not going to see advantage in terms, for example, of model complexity if we try to it's not simple at all, but if we go about the direct solution of trying to find quantum version of a classical machine learning model, probably that will not give us a real advantage. We should start from native quantum algorithms. And then there is the discussion about sample complexity. There are hints from the first tests that have been run that it is possible to actually train quantum machine learning models using a smaller number of, a smaller training set with respect to their classical counterpart. Now, of course, then this has to be related to what it means in terms of generalization capabilities of the model. And then there are a lot of additional practical steps. Do we include the data preparation step into, if we want to measure our advantage in terms of runtime speed up, do we include the data preparation step? We should, of course, because it's a very important step. And this is a step that might take actually quite a lot of time beyond the simple, core algorithm speed up. And of course, all the discussion about using realistic near-term devices instead of ideal quantum devices, because of the presence of error and instabilities at the level of the circuit. For example, the depth of the model that we can explore on NISQ devices is actually limited. Okay, let's see if we can go now to some examples, because I think I spoke a lot and I showed very little. So we have we have results that I try to re-explain in terms of generic problem. So we've investigated support vector machines for classification problems, graph neural networks for pattern recognitions. This is one of the examples that you will see. Quantum Boltzmann machine to do reinforcement learning, and generative adversarial network to do simulations. So I will just talk about what I can talk about, depending on the time that I've left. I just wanted to point out that I'm not talking about the support vector machine example, which has been detailed in a seminar not long ago by Professor Saulan Wu. And so you have here the link if you'd like to listen to that there. So let me start with the pattern recognition problem. This has been applied to particle tracking. It's a very important problem at the level of for the experiment, and it will be even more for the case of the high luminosity LHC. So deep learning models are being tested and are being developed to solve this problem already, and there are many different approaches that have been tested. Graph neural networks are among the most successful. And they interpret basically the problem, the detector output as a set of hits connected by a graph that are then optimized by the network. The model that we use as a baseline is the AppTrackX model, model, which is now become the exact TrackX model. I'm sorry, I will move around. There are references here, which uses a cascade of classifiers that classify the single hits, detector hits, and the segments that connect them. And this is an iterative procedure that works very well, as you see here. Those are very, very high efficiency and purity results that you can get from the classical network. Oops, sorry. What I wanted to say is that what we have done. I'm sorry. This is the quantum model has ended up in the wrong place. But basically, what we have done is replace these structures with quantum circuits, the edge and node networks. Each one of those networks is built using a hierarchical quantum classifier. Now, those are models that were actually defined, were classical models. They used to be called quantum-inspired networks that were run classically and were inspired by quantum systems. Tree-tensor networks and Mera graphs are among those. We tested both. The reason why we tested those is that they, in particular, the TTN network, have been proved to be relatively robust against noise. There have been different experiments that have been run on a relatively small number of qubits, but they seem to be, but they are very, very encouraging. And so we've used this architecture to solve a simplified track reconstruction problem, the same that was, you might be aware of the TrackML challenge that was published some years ago, and for which a specific dedicated data set that was made public by the community. So the results are shown here. They compare the area under curve for the classical model, which is shown here on the TrackML data set, so a simplified data set that is tested with the different depth, go from 1 hidden layer to 5 to 10. And the performance is compared to quantum models. So 3 different hierarchical classifiers, 3 different possible architectures of for quantum classifiers with that are very shallow, that just include structure, sorry, like the one that you see here. Basically, sorry, need to go back 1 sec here. So the initialization of your data with the embedding, a set of entanglement that is realized with CNOT gates here, additional rotation gates and more entanglement, and then another rotation on a single qubit and a measurement. So the performance of the quantum network are close, but not better than not better yet than the classical network. But it's interesting to see that in particular for the TTN and the Mera architecture, the results are not far away. The difference between those architectures is really the amount of entanglement that is introduced in the circuit. So one of the first, I think, how much time I have? Because I think I'm almost at the end of the.
You have 15 more minutes.
Okay, so I can go on. One of the things that we decided to test this summer was to try and see if we could change the representation of the input data in order to improve the classification, the performance of the classifiers. And we decided to look into this because this is also one of the improvements that was developed for the classical model. Now, the problem is defined in its baseline configuration in the original Cartesian representation This is, you see a two-dimensional representation in the XY space. What you can do is to build a multi-layer perceptron, a fully connected network that will map the input data into an embedded space in which the distance between the point is maximized by an inch loss. So this is for this specific example is the result. The procedure is to embed your data with respect to a seed point, which is the starting point for your track search. You can see how in this embedded space, it is possible already to classify the points with respect to their distance from the seed that is represented in black. So in red are the points that are selected as belonging to the same track, basically, and the other colors are not. So if you transform this back into the Cartesian space, into the original space, then you clearly see how you could select the corresponding track, the correct track with respect to the original seed. Now we want to do this. We try to do this with a quantum algorithm, and in particular, we use this example to try and understand how different architectures for the quantum algorithm could, to understand if and how different architectures for the quantum algorithm could affect the results. So the embedding is modified in a way that you see here. The original part here, the MLP, is the same that is used at the classical level, but we introduce a circuit, a quantum circuit in between, and we study the characteristics of this quantum circuit. In particular, this is done according to two quantities. We followed some work that is cited here to do this. Now, the entanglement, we already talked about this. It's the capability that the system has of actually representing correlation that are quantum in nature, that cannot be represented classically. There are different ways that you can actually measure or quantify entanglement of states. This Meyer-Wallach entanglement measure is what is used in this work and what we followed. It is somehow you can think of it as a measure of purity of a state, of a quantum state, somehow. The second quantity that is important is the expressibility. Basically, the ability of the circuit to cover the largest possible area, in the Hilbert space. Okay, and this there are different ways also of measuring this quantity. In this case, a rather simple one is actually just building a distance. This is the standard KL distance between the state and a uniformly distributed random state. Just to make it a little more, hopefully more clear, in case of with a practical example, in the case of a single qubit state, you know that a qubit state can be represented on the block sphere as a vector, basically. In the case of a zero state, this would correspond to a vector that is pointing up. So you can see it represented here on the top of the sphere. If we consider a circuit that it's only made by the identity operations, then the expressibility of our circuit is basically null, because we can't move around the block sphere at all, but we can only represent a zero state. If we include rotation and a Hadamard gate, we are already improving the expressibility of the system, because we are able to move around a circle around the sphere, increasing the complexity of the circuit, we can sample more points. And you can see here how the expressibility changes in these different cases. So what we've done is to test different architectures that exhibit different number of parameters. So you can see here the number of the circuit number, the identifier of the circuit, and we compare the number of parameters, the amount of entanglement, the expressibility, and the time it takes to actually train the overall circuit. I should say that as far as the entanglement is concerned, I never said that, but it's not just a matter of introducing entanglement and gates in the circuit. It's very important, the topology of the entanglement itself. So how along the circuit the qubits are connected to each other. And there are very different ways in which the topologies that can be used to this that will affect this measurement. So in this case, the entanglement, I will explicitly put it here, the higher the better. So the circuits with the larger number here will have higher entanglement level, and in this case, the expressibility, the lower is better. So you might want to have a value here that is as small as possible in order to make sure that you're covering most of your space. So we tried to measure the loss. Yes.
So what kind of entanglement measure are you using?
So we are comparing those 4 different architectures. So as you see, you can have, for example, in this case, a linear kind of entanglement here, where one qubit is connected to the neighboring one, and with the loop over the first part of the circuit. But then yes, it's just the neighboring one, because here it happens the same. Then you have also the hole-to-hole case, which would be here, I believe, because if you follow through all the entanglement gates that are applied here, you will see that basically all possible combination of qubits are entangled between them. This is a hierarchical approach. This is basically similar to the TTN circuit that you saw before. So you always entangle the external qubits couple by couple, and then you disregard them basically. And here there is a minimal amount, really. Sorry, I didn't mean to change. I'm going the wrong way. Sorry. So sorry, does this answer your question? Was this the question?
Yeah, I mean that. So how can you quantify the entanglement?
Oh, sorry, I didn't understand. So what we do, we use this. So this is a measurement. So what you can do is you can look up I can point you to the description, the definition of this particular distance that we use. There are different ones. This one in particular, what you can do is you measure the amount you measure how much. So you have a state, the state for which you want to understand a set of states for which you want to understand the entanglement. You consider a set of basis states, and you measure a distance that is built as a sum of the projections of your entangled state over a state in which you are excluding one by one each one of your basis states. So this is how the difference is built. This quantity is built, and it's a representation. It's one of the possible representations.
No.
I should have put a formula there. I'm sorry.
Second column in your table. That I understand that the DKL, but you quantify the entanglement, right?
Sorry. Yeah. I'm sorry, I was interrupted. Could you please repeat the question? I had to answer the door. So you were talking about the way we actually measure this. So what you do is by sampling you can measure this by sampling you implement your circuits. So for example, circuit for 14, and you sample it many times. And on each one of those samples, and you calculate this quantity on your set of sampled states. Yes.
Okay.
Have I answered you?
Yeah, that I guess that is an entanglement entropy or something. It's not
entanglement entropy.
Yeah, or I'm not sure.
I mean, you can also use measurements that are similar to entropy to measure your entanglement. Yep. This is not necessarily, I mean, again, this is a choice, a specific distance that we do, that we implement.
Yeah.
Okay.
That's true.
Okay. But I'm writing down, I'll look for more citations to add here also for this. Okay, let me show you what this gives as a result. We do see now the error bars that you're seeing associated to the loss functions are actually related to the fact that the training is not stable, it's not very stable, and we need to repeat it many times. And we do actually see, especially in some cases, you can see that the blue curve is one of the cases in which the training is less stable, and you have larger error bars. So this is one of the things. The stability of the training is affected by the choice of the quantum circuit, and also the let's say the behavior, the convergence level. You can see that circuit 14 seem to have a slightly better convergence, faster with respect to the other. And if you go and check, is indeed a circuit that has a relatively high entanglement value and a very low expressibility. So at best expressibility is in this sense. Now this of course is a very preliminary kind of. It's not. I wouldn't consider this a conclusion yet. We are still looking into this, and in particular the reason why, let's say the limiting factor so far as being the training time for the simulation, as I meant before. But it's interesting to see that there are changes in the behavior of the circuit of the training process, depending on the characteristic of quantum characteristics of the circuit. Are there the questions so far? Because otherwise I will change to the generative model problem. Okay, let me just briefly, because I'm running out of time. The generative models are a very interesting class of models. They are they can be used for many different applications, and we are, as a community, investigating them for anything that goes from simulation to anomaly detection problems. In particular, simulation is a very big problem in terms of for experimental physics. GANs, generative adversarial networks, are among the models that look more promising today, and that are mostly being used to do detector simulation. Now, in particular, our group has worked for a long time on a GAN prototype based on two-dimensional convolutional layers that is aimed at the reconstruction, at the simulation of an electromagnetic calorimeter with high granularity, typical of what will be used in future colliders, future colliders. So we use this prototype as a baseline for investigations in quantum circuits. And I really don't have time to go into the details, but I wanted to mention that we tested several approaches. One of them, and the first, the easiest, is a model that has been proposed already some time ago by IBM, which works very well and learns the average distribution from the training data, but unfortunately is not really a generative model in the sense that is not capable of sampling events. What can do is to load in a quantum circuit the average distribution that the circuit that the generator has learned. So we started there, and we worked. Well, here you see an example in 2 dimensions that compares a real image to the average image generated by quantum GAN. We have also developed this, extended, let's say, this model, adding a second generation step, which from the average distribution around or performed sampling. So we did build a real generator model that is capable of reproducing the average energy distribution, so the average image, that is capable of generating samples, and therefore as a very stable training. Those are hybrid approach. So if you might know, you probably know that GAN models, generative adversarial network, uses a configuration in which a generator network is trained against a discriminator network that classifies the data as real or fake, depending if it's a real training data or it's being generated by the generator network. And in our setup, we have a hybrid GAN in which the generator is quantum and is trained against the classical discriminator. We've also implemented this using continuous variables. And in this case, we were able to test both a hybrid model and a fully quantum model. So in the case of the hybrid model, as I said before, if you train a quantum generator against the classical discriminator, what you need to do is to run a measurement at the end of the generator and then analyze this through the discriminator network. If you don't perform your measurement and implement both the generator and the discriminator as quantum circuits, then you can train them both on quantum hardware. I'm flying through the slides because I'm late. The hybrid implementation of a model works very well. We compared very simple quantum GAN hybrid, so quantum generator with a total of 264 parameters that is trained against a classical discriminator with this set of parameters. It's fully connected layers, and you can see here the number of nodes that are used for each one of the layers. And we compared with a classical configuration, so a pure classical network that uses the same discriminator, but a fully connected generator with about 44,000 parameters. Now, you can see that we get very similar results. Here you can directly compare the average distributions. And what we've also observed is that probably because of the difference in the number of parameters of the generator, we managed to converge, the quantum GAN can converge in about 100 epochs, while in the case of the classical GAN, we need to go up to about 1,000 epochs. Which is, I think it's a very interesting result, although it's not really enough to actually claim the fact that we are seeing a model complexity kind of advantage. So let me I will skip this. We try to implement also a quantum discriminator. It works very well if we use it as a generic classifier, but the fully quantum GAN model is not stable. So we did run it, but it looks like we are running into problems of mode collapse. So the fully quantum, so quantum generator plus quantum discriminator model is still not stable. So we are still working on this. So let me conclude. I'm a little bit behind. Sorry about this. So the work that I showed you is part of a much larger initiative that has started at CERN and that goes beyond quantum computing. What we really want to do is to try and build the necessary expertise inside the community with everything that has to do with quantum technologies. And the reason is that the paradigm of quantum computing is very different than what we are used to so far. And if at some point, or when at some point, quantum computers will become more, let's say, more closer to us, more usable, easier to use, we will need practice. We will need to be able to use them efficiently. And this is something that requires time. As this is general, as far as quantum machine learning is concerned, we started simple. What we really wanted to do so far was to try and understand practical aspects of implementing quantum machine learning circuit for problems that we know very well how to solve classically. Everything that you saw so far as a classical benchmark, a classical counterpart that is available, that we can use as a benchmark and we can compare against. So results are very, very exciting. What we want to do now is, of course, continue along this line, but trying to go more into formalizing a formal approach, trying to go further into the direction of characterizing algorithms and trying to understand which problems could actually be advantageous to solve with a quantum approach. Nobody would like to replace a classical deep learning model, DNN, that works very well for a specific task with an unstable quantum circuit. And I think one of the key ingredients into getting there is the idea of exploring algorithms that are not simple translation of classical models to quantum, but to design real new quantum algorithms. And thank you. Thanks for your patience.
All right. Thank you very much, Sofia. It was a very nice talk. Are there more questions? So what people are thinking? Can I ask something about the GAN example?
Sure. I really went fast through it. What would you like to know? So there were actually 3 models in here.
Yeah, I just had a more general question. So the fact that you get mode collapse if you use quantum discriminator and a quantum generator, this could of course also have happened if you use 2 classical. This is more a question of whether the discriminator is much more powerful than the generator. So the fact that you didn't get it in the first case was because it so happened that the quantum neural network the generator was in a sense as powerful as the classical generator. Did you tune it to be so, or did this just work?
No, we did tune it. We did tune it in the sense this is the result of tuning. We did observe in our initial test. We did observe mode collapse. So we had to increase the size of our generator. We had thought, so this is built as a 3 qubits network using 8 layers. So 8. So the unit, let's say the layer, is a combination of gates that performs a set of like translations and rotation, and a Kerr gate, which introduces the linearity. And we have 8 of them that we repeat them. We had started with 3, we went up to 5. We had to go to 8 to actually make it work. So there is, but if you want, there is with respect to the classical case, you have even more handles that you actually need to learn or need to tune or to try. And it makes your tunization more complex. If you look, for example, in the case of the classical GAN, we build a generator that has the same structure as the discriminator. It's a relatively, it's the initial, it's very close to your initial choice usually, right? This is what you would do. You build the balance system. In this case, it's difficult to quantify the strength, so of your quantum generator.
There's a question by Sven.
Hey, yeah, thanks for the talk. I have a question on the GAN part. So is there some work also trying to use flows or respectively invertible neural networks to have quantum versions of those?
Quantum versions of? I didn't
Invertible neural networks.
Not that I know of. I have only recently seen work on invertible networks. In particular, there were some interesting talks that were presented at CERN at the IML workshop. Those were classical networks, and for me, I mean, I had no experience with that before, and I didn't look. So I don't have an example of those in the quantum.
Yeah, because I mean, from the design perspective, they should really well fit into the quantum way of writing down all algorithms, because you basically, when you have these kind of box structures, so you could really nicely replace them with quantum gates in principle, I would think.
Yeah, no, it's an interesting point. I just simply never came across, but it could be that there is already some work in that direction. It seems reasonable. Good point.
There's another question by Filippo.
Writing down.
The first graph in where you showed the eigenvalues of the neural network.
I can't really hear very well. It's low, like the volume seems.
Slide 6.
Slide 6. Let me go this way.
11. Sorry.
Slide 6.
No. 11.
Here, you mentioned eigenvalues.
Yes, exactly.
Yes.
So I wanted to briefly ask what is the meaning of the eigenvalues? So of what are the eigenvalues?
So this is the SCM matrix, the SCM matrix that you can build from your quantum input state. So there is actually a not so simple procedure that you can use to practically calculate these matrices. But what you do is you embed your classical data, you create your initial quantum state, and then you build SCM matrix that corresponds to, I forgot the name, it's an index that you use it's coming from information theory. I can look it up for you because I don't remember the name really. But what it represents is the shape of the SCM of your gradient in the quantum input state, the phase space.
Okay, and concerning the classical network, what like operator are these eigenvalues taken from?
It can be built in a similar way. It's not necessarily related to the fact that this is the Hilbert space. You can build it for a classical phase space as well. There is the corresponding version. There is a corresponding version that can be built.
Okay, thanks.
I need to, again, I need to go and look into the details myself.
Okay.
If you want to know the practical steps to actually build this.
No, I just was looking for an intuition maybe for the.
Oh, but you can. It's the whole procedure is explained in the paper that is presented, and there is even access, if I don't remember wrong, to the code.
Okay, thanks. Then I'll look it up.
Can I ask another question? In the beginning, you had this outline when you go to a Halloumi LHC and late 20s or so, you had this extreme increase, and then you had
this. Or the high Lumi schedule?
Yeah, exactly here. So you had this, not the other one where you were showing the flat budget.
Yeah.
So this is how many petabytes of data you can process in 2030 if you assume this 20% increase per year, or?
Yeah, so you can make the calculation if you think that today we are storing, we have in the CERN Computer Center, we have stored so far 330 petabyte of data. So this is the line that considering a flat budget is estimating the capabilities based on what we can do today. Now, both in terms of data storage and in terms of CPU and the consumption, you can see that, well, those different colors are just referring to specific different kind of data, so data format or tasks. You can see that we are talking about like in total at the beginning of the run, if we stay, let's say, to the minimum level, we are talking about more than a factor of 10, which will go higher and higher. I mean, this is the requirement, and what you would see is something that is maybe twice what we do today instead. You see here.
So would the idea be that if we manage to increase the computing techniques, then we could take all of this data into account, and if we don't manage, we have to?
No, well, there are different things, right? The quantum computing it's a long shot. I mean, if you look at here, the real schedule now for the high luminosity LHC is 2028. It's not 2026. Yeah. So, but so it's not likely that, for example, we will be able to move. Not for example, it's not likely that we will be able to move our data processing chain to quantum computing in 2028. Even if algorithms can be developed to solve this problem, the size of the problem itself, of the data that can be processed by quantum computers today, it's not comparable to what's produced by our experiments. And there are a lot of different other different practical problems, engineering problems, how you actually access, how you load the data. So the problem that you see here, the computing problem for the high luminosity, is not going to be solved by quantum computing. There are other strategies that we are looking at, and actually classical deep learning is one of the major solutions probably to this, because you can process data much faster. Because, for example, because those are algorithms that are naturally parallel, while today most of the high energy physics code is not capable of using HPC resources. So migration to HPC, for example, even the fact of using generative models for simulation would have, for example, if we manage to speed this up very much, we could get into the possibility, into the configuration in which we decided to, we could decide to simulate data on the fly without the need for storing it. And you can see here, no, actually here there is no difference, sorry. In this plot, it doesn't show the quantity of data that we store for simulation, but this is roughly half. Basically, for as much real data that we store, we need almost the same amount in simulation. If we can avoid storing that because we just produce it so fast that we don't need to store it anymore, then that's another, for example, another solution. But quantum computing, so the problem is there, and it's triggering the search for new technologies, and quantum computing is among those, but it's not going to be the solution.
All right. I can't see any further questions. So we all thank Sofia again with our clap emojis, and I clap.
Thank you.
Live. So yeah, it was a very great talk. Thank you very much.
Thanks, and I will send you the slides.
Yeah.